Thank you, Chris, and thank you all for coming today. So yes, as Chris mentioned, in my work, I study the behavior of songbirds, specifically the vocal behavior of zebra finches in a lab setting, as you can see here. Zebra finches are native to Australia and Indonesia, but you can also find them in quite a few labs because they've become the model organism for studying vocal learning and its neural substrates. So vocal learning is the capacity to modify one's vocalizations in response to auditory input. This is a really important ingredient in language acquisition, and it's also quite rare as far as we can tell. So among mammals, whales and dolphins have it, some bats, but our nearest primate relatives do not. And songbirds are actually the most species-rich group of animals that are vocal learners, but most of what we know about the song system in the songbird brain, and here you're looking at some of the most popular circuits, comes from studies of zebra finches. Specifically male zebra finches. So females have different brains and they don't sing. Each male zebra finch sings a unique vocal sequence that he learns, and we call this his song. I'll play the example for you again at half speed in a moment, so you can perhaps get a better sense of what the chorded female hears and also pick up some of the subtler acoustic structure in the sonogram, which is a visualization of sound that you can read sort of like a musical score left to right. Here we go. Hopefully, among other impressions, you can both see and hear the repeating motif structure. The bird acquired his song motif when he was young by copying an adult model, typically the father's song. As you can see in these two sonograms, imitation can be highly faithful. This is the outcome of a 2-month-long slow matching process, which coincides with sexual maturation and begins with juvenile babbling. Much wonderful work has been done over several decades, mostly in individual zebra finches, to explore the intricacies and neural mechanisms of vocal learning. However, in the course of this research program's development, the phenomena under study have become oversimplified to the point of distortion. So first, many people will say that zebra finches are so great to study from a motor learning perspective because, unlike some other species, their adult songs are so simple and so stereotyped rendition to rendition. Second, a picture has emerged of vocal learning as for producing accurate imitations. Today, I'm going to show you some ways in which these myths misrepresent the animals that they've been built around, whose songs are not, in fact, stereotyped, and whose vocal learning is socially motivated and includes learning how to communicate. In many ways, these observations are not surprising. What's surprising is that they've been ignored. Zebra finches are highly social animals. Unlike many migratory songbirds, they live in long-lasting nomadic groups. They're not territorial, and these social groups are the context in which they learn their songs. The focus on song imitation, learning what to sing, ignores the problem of learning how to sing in terms of vocal coordination, which may entail group norms regarding turn-taking, and may also depend on individual plasticity and adaptation. So my proposal is that while vocal learning studies have relied on an oversimplification of the natural behavior of these animals, the sociality of zebra finches makes them a really good study system in which to look into something else, which we might call improvisation. And I have 2 guiding questions in my research. This is work that I've been developing together with my PSSN mentors, Peter Behrman and George Lewis. First, how do birds sing in social interactions? And second, how do social interactions influence song development? We know that when a male is at his most aroused in the courtship setting, his song is faster and its elements become more stereotyped in terms of their acoustic structure. Historically, attention to context-dependent effects have largely been limited to contrasting this highest intensity female-directed courtship song with song when the male is alone, which some people call practice song, and typically neglected is the fact that male zebra finches readily sing in social contexts outside of the courtship setting, including when there are no females around. So 3 male zebra finches in the lab. As I showed you before, zebra finches' songs have a repeating motif structure, and the motif is the largest unit which can be considered to be stereotyped. But zebra finches do not produce isolated motifs when they sing. Song has a higher level structure, which is the song bout, and each song performance begins with a series of accelerating short calls, which we term introductory notes. The number of repetitions of motifs is variable, as well as the silent gaps linking motifs and various other call elements that can be inserted. And so this structure is not stereotyped. Compare this. With this. Very different songs from the same bird. In order to visualize this bout structure and its variability, we can take an analog rather than symbolic representation of the song bout by extracting acoustic vectors of acoustic features. So in this case, pitch. And you're looking at a color scale that indicates the song's introductory notes in red. We can do this with many song bouts and align them all to the onset of the first motif. And with a large enough sample, 400 renditions stacked one on top of each other here, sorted by bout type, we can see that indeed song bouts exhibit structure beyond the stereotype motif. If you focus between the 0 and 1 second mark, you can see these uninterrupted vertical columns of color. Those show you the stereotypy of the first motif, which ends with this golden colored element that's a harmonic sound of around 600 hertz, after which the bird has different options. He can either stop singing or go straight into another motif, connect his motifs with one or more introductory notes, or use these orange calls that you see on the bottom. The motif is stereotyped every time it occurs, but you can't see the vertical shape beyond the first motif because the timing varies. So even if we sort representations like this by bout duration, we can see that bout repertoires vary across individuals. These are 4 snapshots of the repertoires of 4 different birds, which we can rank according to how much variability they have in terms of sequence, but also timing. This is a different color scale because I'm using a different acoustic feature here. Wiener entropy is a measure of tonality. Interestingly, these bout structures are not imitated. So these are actually the mature repertoires of a tutor and 3 of his adult pupils, his former pupils, and the tutor's bouts are actually the most variable. And if you look at his best pupil in terms of motif imitation, which is quite perfect according to the sonogram, they have very different styles of singing as reflected in these bout repertoires. And the songs sound different too, which is obviously more important than how they look in these plots. That was the tutor, and this is pupil 1. Pupils 2 and 3 have more different variations on the same family theme. In order to investigate this plasticity, how this plasticity gets expressed in social interactions, I analyzed the expressed bout repertoires of 7 individual birds from an established social group in all possible pairs. And the first finding is that singing amount varies by partner. So although some birds do sing more than others overall, all birds sing more with some partners and less with others. And also we see some symmetry around the diagonal. which indicates a matching singing amount in terms of interactions. For example, A and C, A and G, B and E, and B and F. And still, there are also phenotypic differences. So, for example, bird D tends to elicit very few songs in his partner, although in most cases, not by singing very much himself. But for this talk, I'm just going to focus on bird A, our chattiest bird, who tends to sing at least as much or more than his partner, and we're going to examine both his expressed repertoires and those of his 6 partners. So here they are. What we can see here for bird A is that a bird's expressed bout repertoire can vary quite a lot depending on who he's singing with. And you see these changes in the changes in the shape of the distribution, which are due to over and underrepresentation of specific bout types, which you would not obtain by different random samplings of the same distribution. These are the songs of his partners. And I think just in the most gestalt visual interpretation here, there are some suggestive similarities between the 2 columns. For example, perhaps bird A sings short bouts with E because E sings short bouts. Well, actually, bird E sings much longer bouts in another context with bird D. So this raises the possibility of convergence due to mutual adaptation within a pair. And we can actually describe the social network by continuing to build it out pair by pair. And I won't make you study all this data. I'll do it for you. But if we want to understand why these production differences arise, we need to use a finer time scale. So here are snapshots of 2 pairs, again featuring our focal bird A. If you compare the top left and the bottom left panels, we see that A's songs are more variegated with bird C and more regularized with bird D. And here you see the songs in each pair now organized chronologically with bird A red in both panels. And we see that A and C alternate much more than A and D. This is because A and C are actually taking turns, which you can see from the real-time visualization of the song bouts on the right, where I've added the silent intervals back in. It sounds like this, an interaction sounds like this. And bird C jumped in again at the end. A and D sing in segregated epochs and also with much less density. Measuring the latencies between bouts of each partner, we find that A and C are matched, each lagging the other most commonly by just a few seconds, whereas the distributions of latencies for A and D have no clear peaks. But also, bird A spaces his own bouts differently in the turn-taking interaction with C. So he not only sings more variegated bouts, but also more tightly sequenced, which is maybe not what you would expect. You might think that as 2 partner songs become more densely interleaved, they would simplify in structure, but that's not what we see. So to sum up this brief overview of this part of my research, I hope to have convinced you that zebrafinch song is not actually stereotyped unless you define the behavior in a highly restrictive way. And I've presented some evidence that suggests that this variability may actually be socially meaningful and not just noise. This is just scratching the surface of the behavioral flexibility and social dynamics of these animals. But in the rest of this talk, I'm going to tell you about a parallel line of my research in which I'm looking backward at ontogeny in order to begin to understand the social context of song development. Song learning is a social process. Juvenile zebra finches learn their songs through social interactions with an adult tutor. However, the tutor is not actually necessary for this learning to occur. Young birds can learn from exposure to playbacks of the tutor's song alone, and this has allowed us to test hypotheses about vocal learning under controlled conditions. So in designing such experiments, we have learned a few things about optimizing the learning environment. In particular, giving birds operant control over playbacks leads to better imitation than passive exposure alone. So this is what I mean by operant control. bird presses on the key and he hears a song, and the song is its own reward. There's no food coming later. The other finding that's important for what I'm going to show you next is that a limited playback quota is also better for learning. One possible reason for this is that it contributes to the bird's motivation to learn. So in this study, I decided to see if we could learn something about motivation during song learning by analyzing the keypecking behavior in this kind of operant song learning setting. So we limit the number of daily playbacks of the tutor song to 20, which is much less than the normal vocal output of a zebra finch. They typically can sing hundreds, thousands of songs a day. If the juvenile bird presses the key beyond this 20 playback quota, nothing happens. Birds discover the contingency on their own, and they can potentially control the rate of playbacks, but not increase the total exposure. So we are interpreting pecks when the keys are not active as an indicator of how motivated the birds are to hear this tutor song. And I record all the keypeck events. I also record all the vocalizations throughout development. In this plot, each tick mark represents the number of keypecks per minute, with each day occupying a row and chronological age running top to bottom. So clearly this bird is exceeding his 20 playback daily quota in terms of keypecking. There are even some minutes where he pecks the key 20 times, even though he's already exhausted the quota. Still, there are fluctuations, so there are distinct epochs over the course of development with transitions between periods of frequent keypecking, relative quiescence, and you can also see this. It's okay, there's one thing. There's a ridge here. That's increased keypecking activity when the playbacks turn on, when the keys become active. One way we can quantify this activity is by measuring the gross rate in number of keypecks per day. And so I've flipped that and added back to the raw data visualization. And all this time, the bird is singing, his song is slowly maturing, and we, of course, want to know whether and how the key behavior has a relationship to song development. In this example, we do in fact see a correlation. So if you look at this trough in keypecking activity between days 78 and 89, the bird has already acquired a stable song imitation by this time, and he doesn't make any further changes during this period. However, he's not done. Suddenly, within just a few days, his song undergoes a revolution, and this coincides with a sudden increase in the keypecking activity. So we can track motivation over development, both in terms of overall rate and also the pattern of how the activity may be distributed throughout the day. To do this, I use a measure of burstiness. And in this example, these two measures are roughly correlated, but here in a different bird, second bird, we find a spike in burstiness around day 90 while the rate remains elevated. For this bird, this sudden change in keypecking activity accompanies the appearance of a brand new song element that didn't exist before. And this new song element crystallizes in acoustic space while the keypecking activity remains bursty, and then after it finishes maturing, there's a sudden drop-off in apparent motivation to hear playbacks of the tutor song. So this is a third example. Some birds press the playback keys seemingly almost as much as possible. They're alone in the cage, as you may remember, except you can see that there's this widening pleat around 4 p.m., which corresponds to the beginning of the afternoon playback session. And this results in playbacks being delivered at a slightly slower rate, beginning around day 100. So importantly, after this time, the bird is still getting his full quota. He's just getting it moderately less rapidly. And what is he doing during this time? Well, he may not be pecking frequently when the keys become active, but he's pecking with precise timing, as you can hear in this example. It begins with, that's a juvenile bird. That was the sound of him hitting the key and then hearing the tutor playback. And looking into the sound recordings, we find many more examples of this pattern of co-singing with the virtual tutor happening again and again. Not all birds seem so attuned to their interactions with the virtual tutor. Some birds, like this one, this is a fourth example, have a low appetite for the tutor song even after they learn the contingency. So they're in no rush to burn through their playback quotas, unlike the previous bird. We can dichotomize birds into slow and fast learners in terms of how well they acquire a good imitation of the tutor song at an early age. And when we compare the playback appetite of slow and fast learners in a total of 45 birds, we see that the two groups, slow and fast learners, segregate according to their motivation to hear playbacks of their tutor song. So in this second half of the talk, I've presented evidence that vocal learning is socially motivated, and that this motivation not only tracks with vocal development, but may lead to the development of patterns of interaction that underlie the establishment of a social relationship. In other words, birds are playing an active role in their own song development. And there's a lot more to be done. What's next for me? We clearly need a better robot. So hopefully soon, George and I will start experimenting with our first Voyager-inspired Avian interactive acoustic system with real birds. And I think I will end with my assertion that zebra finches are improvisers. This is based on my observations of their vocal flexibility and their social motivation to learn.